of you yesterday were present, I think at least 5 or 6 of you who took this advanced CFD course last week, and most of you have come for this particular course, and as I can see, it is a completely full room and there are about 65 people. Now, before I start, I think that it may be worth taking a few minutes so that I know what the level of expertise you have, so that I do not want to explain and do things which you already know, and on the other hand, I do not want to make the subject matter quite complex, so that it is all the lectures are in the late afternoon and you may start sleeping in the lectures. So, I want to keep a good balance of the lectures, and that is possible only if I know that what kind of background and what kind of interest you have. Now, all of you are given a handout, a printed booklet which has information about the course material. So, you can see that there is a lot of course material that has been given to you in the booklets, and I think that only 60 were printed. So, some of you may get it tomorrow, because they did not anticipate that there will be so many people. The second thing is that I have purposely not covered topics which are mathematically very complex, and so they are not a part of your booklet, but they are very complex in terms of the mathematics and also how do you numerically solve that aspect of the problem. And so, as a result, you will find that, but if you are interested in your research, those part which I will briefly mention, but not discuss in detail, then I have information and I will be happy to share with you. Because if I had included everything that I know, then the size of the booklet will be double, and also the time is still very short in terms of what we want to do. So, although you may have a lot more material and there is a lot more slides which are available, but it may not be a good idea to cover everything, but rather to cover a smaller number of slides and a smaller material, and you can always look in your handout what is given to you, and then if you have questions what we covered today, you can ask tomorrow. You can ask tomorrow first 15 minutes, let us keep first 10 to 15 minutes every day for next 5 days or 6 days, that we can discuss, which means that after dinner every day you have a homework that you go home and study and then ask questions if you have tomorrow morning and tomorrow afternoon, and we will maybe follow that. Of course, you are always welcome to ask any questions that you may have. You can stop me anytime, raise your hand, and I will try to do my best to answer the questions. If I do not know the answer, I will tell you I do not know the answer, and then that will be my homework to go home tonight and see if I can find the answer. Because knowledge gain and knowledge is always a learning experience. It is never stops. Some of the courses I have taught for 20 years, and I suddenly find that somebody asked a question which I had never thought could be a part of the course, or could be so penetrating and so thoughtful that it takes a time to figure it out. So, that is what is called inquisitiveness, or looking at a problem from a different angle. So, most of you are young people here, and that is a good thing. As the director said that when he looked at multiphase, and he is a electronics engineer. So, that is what he understood. All right. Can you tell me why he understood multiphase as an electronics engineer? So, the AC current is a 3-phase. So, that is why he thought that DC current is a 0 phase. So, he thought that multiphase means that there is a 3-phase AC current. I understood what he meant. All right. So, as I was thinking, that we have a very small part of the phase. So, you can consider a multiphase flow where most of the medium is a gas with a few particles flowing, all right. But it is just to keep you little entertained, there is nothing more to this, all right. So, as I said that if you look at it, we will go over slowly and cover as much as we can. Now, of course, today we have already spent an hour or more of our schedule, but that is an important part also to go through that ceremony, and that is a tradition, and there is a lot to be said about the tradition, but it is a good tradition that I think we should do every day, so that I have to teach 1 hour less. All right. So, any tradition that is helpful to me, I think I like that tradition. So, you have all this information, and as I said, we will proceed, and I will sit down if you do not mind, because I have some pain in my knee, and it is more convenient for me to sit down instead of standing 4 hours, but please do not hesitate to stop me wherever you think there is a need to stop. See if we can. Okay. So, that is the title of the course, and so we will start with lecture 1, and so this is going to be the course outline for next 4 days, next 5 days, and I think last day there is a small quiz. I have not prepared it yet, which is a requirement also to test whether you have understood anything, and on that basis of quiz I think they probably give you a certificate or something. So, we will start with lecture 1, and then we will discuss some definitions, terminology and other numbers, and then we will talk about multi-phase flow in a pipe, which is I think a very old problem, and people are still working on it. So, from the experimental work that was done on multi-phase flow in pipes, and primarily flow visualization and some measurements, and after that now people are trying to use CFD to basically work in that area. Now, multi-phase flow in pipes is a very important problem, because in a lot of engineering applications you see the pipes are very prevalent, and of course, the human body inside you have nothing but pipes, right, and all these pipes have a multi-phase flow. So, whether you have a cardiovascular system, or you have a respiratory system, or a urinary tract system, or even a digestive system, is some kind of a multi-phase flow. And similarly, in a lot of industrial applications, whether they are sewer lines, or they are water pipes, or all kind of applications that you see every day in industrial applications, there is multi-phase flow. So, multi-phase flow is actually very prevalent in nature. There are very small number of flows which have pure single phase, all right. Even in this room, there is a multi-phase. So, you have primarily air, and there is always a small number of particles, and that you can call aerosols or some kind of a dust particle, or some particles are always floating around. Now, they may not be important, because the concentration is very small, they are very dilute particle. So, for all practical purposes, the behavior of air in this particular room is a single phase flow. So, that is a very big approximation that we are going to talk about, and that is a among the two phases, one phase is very dilute compared to the other phase, and we are then going to talk about a very dilute phase of flow, and many of you might have heard of nanofluids, where there is a lot of research going on. The reason that I have chosen to be next topic is because that can be considered for all practical purposes a single phase flow, and you can get very good answers. So, we will move from there to single phase flow, and then we will do primarily the fifth lecture. I think is going to be most important. So, if you look in your notes, you will find that will describe that what are the latest development in latest development in the new technology ideas for modeling multi-phase flows. And as a matter of fact, we will discuss some numerical schemes that will make it possible that if you wanted to write your own code, you can do that. You cannot do in a day, but you can certainly do it in 6 months or a year or something like that. Okay. Many of you are teaching, so find a very good student who is hardworking, who is intelligent, and they can do it in about 6 months to a year. So, that is going to be the most important part. Now, I want to mention that what is the main difficulty in a multi-phase flow compared to a single phase. What occurs numerically as well as mathematically? If you have, say, gas and a water or a liquid, what is the most important thing that occurs in a multi-phase? A simple two-phase flow, whether it is in a pipe or it is in a turbine or it is any other system. Let us say you have a simple gas and a liquid. Okay. What can occur? What is the most difficult part from a single phase? The most difficult part is the interface. There is an interface between the liquid and the gas. How do you characterize that interface? That interface can be a moving interface, it can be a curved interface. So, suppose you have a gas bubble, it is surrounded by a gas and inside you have a bubble. What is the most difficult part is to describe the interface of the bubble with the outside gas, right? How do you characterize that? So, suppose many of you may be using ANSYS Fluent or CFX or COMSOL or many other solvers which are available commercially. How is it characterized? Interface between a liquid and a gas. And as I said, that interface may be moving, it may have different shapes as the flow evolves, as the flow moves. Or one of the interface that we all know is very common is the interface in a flowing river or in an interface over an ocean. And what is that interface? That is the interface between water and air, and that can be curved also, that can be moving also. So, how do you characterize that interface? What is the method that is used in any of these codes to characterize the interface? No, source terms where? So, there are various models. So, let us say that you can characterize the liquid phase by some momentum equation, and you can characterize the gas phase by some momentum equation. Okay. Of course, mass transfer has to also be accounted for by the conservation of mass, right. But the interface will define whether the liquid is larger because of the movement or smaller. Similarly, gas is larger or smaller, right. So, that interface is defined by some equation. how do you solve that equation? What is the method? It is called the volume of fluid method. VOF is the exact method. All right. So, that chapter 5 that I am going to describe, I will go into that detail. What is the other than single phase problem? When you have that interface, what is the physical quantity that is a special characteristics that comes in majority, not all, of the multiphase flow? So, like you have viscosity, right? Every fluid has viscosity. You have density, every fluid has a density, whether it's single phase, it has a density, right? Air has a density, air has a viscosity. These are two common fluids, okay? You can have oil if you want, but let us keep things simple, all right? In a multiphase, you have, let us say, oil and water, liquid and liquid, or you have a gas bubble surrounded by a liquid, all right. So, you have a liquid column in which gas bubbles are moving. So, you have a gas and the liquid. What is the other physical quantity that becomes important? Surface tension. So, surface tension is a part of the equations that we will discuss. Okay. So, when you are talking about momentum equation, what does it have? What kind of forces does it have? Pressure force, which is a normal force. Viscous force is tangential force, and what other force? Gravity. In case of multiphase, what is the additional force that becomes important? Surface tension. So, then we will take the surface tension equation at the equations of momentum and add the surface tension, and then we will say how do we apply the volume of fluid method VOF to solve a number of problems. So, what we will do is that in chapter 5, which is a very important one, and it has about 120 pages, it used to have about 200, I cut it down to 150 to keep it simple, and I actually have a code also written by my students that can solve this, and that code, you know, is an example that if you want to write your own code for a simpler problem, not very complicated, you can do that. But this is all available in the standard software that you have. What is the another method that has come along in last 10 years and which is a very important and a very good method? So, one of them is, of course, you said VOF, volume of fluid. What is the other one? Level set. So, it is called LS. So, the level set method is the other one, which is a very complicated method, and I will discuss that. So, I will discuss the VOF, I will discuss the level set, okay, and I will not discuss to so much detail that it becomes too complicated for you. How many of you have heard of VOF? So, you see that it is good that a lot of you know. How many of you have heard of level set? So, only a few people, all right. So, I will give you enough information so that you can see what is the basic fundamentals are, but to go into great depth of it, you know, it requires at least a week to explain that, okay, but you will have enough information that you can move forward. What is the other method earlier than both of these? No, Lattice-Boltzmann is a altogether different technique of solving the even the single phase flow. Lattice-Boltzmann is a methodology. You see, what are the methods to solve the fluid mechanics equations? Finite difference, finite volume, finite element. In the same category is Lattice-Boltzmann. It is altogether a different way of solving the problem, whether a single phase or multi-phase, but the essential element you will have to bring in the Lattice-Boltzmann also. And what is the essential element? VOF or LS? you cannot get rid of that whether you use lattice Boltzmann or you use finite volume, finite element. Those are the fundamental things that you need to include the effect of the surface tension forces and to calculate the interface. Interface between the two mediums, liquid gas, liquid liquid, whatever you have, and we are talking right now two phase to keep things simple. We do not want to add unnecessarily third phase and so on. Okay. Now, of course, you can have also a phase that as I mentioned like air and water, that is gas and liquid. Then you can have oil and water, that is liquid and liquid. But you can also have a cold particle in air, and that is what is used in boiler, in combustion, which is a very important problem. In the energy generation, the boilers are very, very old things. So, how do you use the cold particle? Okay. Now, what are the methods for doing that? Okay. So, what are the methods if you really want to be very, very accurate? So, if the number of cold particles is such that is only 10% of the entire volume and 90% is air, do not become too complicated. Life, always keep life simple if you can get a right answer. Okay. My philosophy is that if you have some kind of a external power and that external power can give you the right answer, you do not have to use any code at all. Okay. You just tell me the right answer, that is good, but you have to justify and you have to be confident that this is the right answer. Okay. So, they keep things simple. So, if it is only 10% of say cold particles in a medium of air that you need for combustion of coal. So, there are now new technologies, oxy-combustion, chemical looping combustion which are more environmentally friendly compared to the boiler. Then how do you characterize that? So, then if you want to follow each individual cold particle inside air, let us say, or gaseous medium. Of course, in air, if you have air, what would burn the particle? Can you tell me what would burn the particle? You need oxygen. Oxygen is the only part, and nitrogen will just leave itself. Nitrogen will never burn a particle, right? So, the question is that if you have a cold particle and it is not 10%, it is 40% of the whole mixture, which means that the liquid, the solid particle and the air mixture is not dilute, but it is a dense mixture. So, in order to understand the physics and the behavior of the combustion of the cold particle with the oxygen that is available in the air, what is the method that is used? That is one of them, DDPM, that is correct. DPPM is one of the ones, and if it is more dense, then what do you use? Euler is not dense, it is dilute. DPPM is middle, not too dilute, not too dense, and that is what is called the discrete element, and that is you follow each particle. So, we will touch upon all these things as we move along, a little bit of these ideas that when do you use what. We cannot cover every method in detail, but we will discuss that. So, what I am trying to tell you is that the chapter 5 is going to be very important, because we will discuss the front tracking, that is the one that I was looking for. So, front tracking method, which is the oldest method, then VOF, the volume of fluid, and then we will discuss the level set, and then as we move along, then we will talk about also the DEM and the Euler or what they call it 2 fluid method or DPPM. You know, there are a number of variations of that. And then we will show 4 applications, and so all of them are multi-phase, and there are all other applications, but I picked 4. The most important application that you will find is the droplet simulation. The droplet is the one on which most of the books have been written, and I have brought a copy of a book which many of you are familiar, is a very basic book, and it is a introduction to multiphase flow, published by the Cambridge University Press, and it is by Christopher Brennan. And so, in the first course, this is the book that people use, but this particular book does not deal with level set at all. It talks about a little bit of VOF, but 90% of the book is devoted to droplets. Okay. So, Christopher Brennan, Brennen, he is a famous person and he is from Caltech, and I think he retired many years ago. But this is the book. But one thing I want to caution you is that if you want to learn about droplets, this is the best book. And if you want to give a course in droplets, this is a very good book. But if you want to learn level set, it does not have it. And also if you want to learn about other things, which I think many of you may be interested in, and we will talk about that, and that is the next application is cavitation. Cavitation is a very important phenomena. I want to know how many of you have heard of cavitation. So, quite a few of you have heard of cavitation. So, cavitation occurs in turbo machinery is very common. There are lubrication devices in mechanical engineering like a hydroviscous device. There are so many places hydrofoils. So, what happens is that cavitation is nothing but the formation of small little bubbles. And so, in turbo machinery what happens is that if you have the cavitation, it causes corrosion, it reduces the efficiency of the turbine, and so cavitation has been, people have been working on it a very long time. So, cavitation has two liquids, two phases. What are those two phases? One is those little gas bubbles, and the second liquid, and most of the time what liquid is that? Water. Water, primarily water. Now, maybe you can have other variations, but this is primarily the case, like in water turbines. And additionally, cavitation occurs in water turbines, centrifugal pumps, and so on and so forth. But of course, if you have a gas turbine, then you have a different problem. But their cavitation is not as intense a problem as in the case of hydro turbines or centrifugal pumps. As I said, that if the cavitation in a particular problem, say, is only 2%, do not be bothered about it, because you are wasting time to get a very little new idea. But if it is a hydro turbine or centrifugal pump, it is a very, very critical problem, because the life cycle reduces, the corrosion occurs, the efficiency reduces. So, if the cavitation is an important phenomenon in that, or hydroviscous drive, for example, which is like the clutches, and wherever you have these lubrication, it can occur, and that means that the effectiveness will go away. All right. So, like if you have a car, I do not know how many of you have a car with a clutch, but nowadays people like to have an automatic drive. Okay. But old fashioned, you have a clutch, and a lot of machinery has clutches still to bring two components together, right. And so, they have this lubricant, and lubricant can undergo under certain RPMs or rotations some kind of a cavitation. So, that is the second thing that I will cover, and the third one is the sequestration of carbon dioxide from the atmosphere underground, and that is become an important topic, because we know that carbon dioxide is causing global warming, and global warming is going to impact the climate, and climate means that if the climate becomes warmer, it will have all kind of devastating effects. Okay, we have heard about that. So, in this case, the multi-phase problem is very different. Okay, of course, again, what are the two phases in this case? Carbon dioxide is one, and the other one is water. But in this case, no, that is a separate thing. I am talking about only the phases. So, carbon dioxide it starts in a supercritical phase, then it can go to the liquid phase, then it mixes with the brine. Brine is nothing but sodium salt, NaCl, solution of sodium chloride, which is there underground. So, then they mix together, and then of course, the other things happen. So, then you can add whatever you want, So, whether so you have to have a porosity, you have to have the permeability of the rock and all that, they have to do with the other aspects of the problem. But the two phases are CO2 and the brine. Okay. So, I am going to discuss that, and I think some people like here Abhishek Gupta is very interested in doing research and doing PhD in this particular topic. And the third one is I am going to talk about a combustion, which is again a effective way to capture carbon dioxide, but here we will have a coal particle, and then the coal particle then will interact with the air or oxygen. So, the two gases will be this, but the whole philosophy will be very different. So, in order to do this and in order to make this feasible, what we are going to talk about is what is called a fluidized bed. How many of you have heard the name fluidized bed? Okay. So, I think there are a lot of people who are already familiar with a lot of this information. So, which means that it is a good thing that almost on every topic we have people who know about this, and so in case you cannot follow everything, you can also interact with each other to follow more. I am going to be very lucky if I can cover all these topics with the amount of material that you will have. But if you went through all these topics and all the material that you have, this book has only one topic, okay, and also it does not have the details of the numerics. It is primarily analytically oriented. So, most of the stuff that you will see is not given in any single book at all. And as I said, there are many other topics, because multiphase is a very prevalent topic or a very prevalent state in the entire universe. All right. I mean, you could have the entire biomedical engineering, which is a multiphase. All right. So, now blood, what are the two phases there? Plasma and the platelets. So, I think that that is what like urinary tract, you have water plus other material. Even your digestive tract and intestines, you have like a slurry flowing into the river. Okay. So, it's all kind of phases can come along actually as you go along. So, we will try to cover these 9 topics, and as I said that we will skip quite a bit, because the idea here is to give you less information in terms of the presentation, but all the other information, if you want to follow it, you will have in the notes that are being handed out. And in top of that, if you want more information, then of course, you can use that and get from the literature, or you can contact me, because as I said, it is not possible to include everything. So, these are some additional advanced books that are given here. Brennan's books is not mentioned, but there are other advanced books that have come along, and they basically talk about the heat transfer, and most of them discuss two-phase flow, because if you understand two-phase flow, then you can understand later on three-phase flow also. But it turns out luckily that all the examples that I gave you, the majority of the important flows are two-phase flows. Huh? Somebody said something? There are very few cases where the flow is relevant to be 3 phases. Okay. And so, I think that is why you see all the books that you have and other details, they are all 2-phase flows.
Have you come across any book related to the numerics of droplet other than the Fluent user guide?
So, as I said to you that this 5th topic, it will have detailed of the numerics and how do you deal with the interface, the level set method, some details of that, some of VOF, and VOF is a part of the Fluent. So, if you read the Fluent user guide, you can of course understand VOF, but it does not contain LS or level set. So, but once you get the information from here, then after that if you use the Fluent guide, then it will be much more helpful for you to understand that. Okay. Any other question or comment? Okay. So, a lot of these things have the details that I have already discussed. So, we can move a little bit faster. So, what is a multiphase flow? As I already said, it consists of the other phases of material. So, material basically has two phases and three phases, that is gas, liquid and solid. But what can also happen is that in some problems the phase can change. So, like if you have initially a water and some gas, all right, but because of the heat transfer the water can change the phase to steam, all right. So, initially you may have water and steam, but then later on you can have more steam and less water. So, the phase can change in there, and also it can happen is that two phases can react with each other. So, like there are miscible liquids, they can mix, but they are immiscible liquids, like oil and water never mix, right, but there are liquids that can mix. So, the phases can change, like if you have a salt water, for example, the example that I gave you of sequestration, you have two phases, CO2 which is supercritical, which is a gaseous phase, then it becomes subcritical, it can turn into a liquid phase, and then depending on the heat transfer, all kind of changes can take place. So, when we are talking about these are the three basic phases of any material, even steel has the three phases, the solid, and if you put in enough heat it will become a liquid, and if you become more heat it will become the vapor, all right. So, every material exists only three phases depending on the temperature and pressure, all right. So, depending on what problem you are looking at, there could be a change in the phase itself during the flow process. So, that is something that one has to be cognizant of, and the chemical properties of the material can also change, because what happens is that if the two materials are reacting with each other, then as a result of that, whether the exothermic reaction or endothermic reaction between the two materials or two phases, you can have some change. So, and then whether there is a miscible liquids or immiscible liquids, so all kind of possibilities occur, and those possibilities are very important because the interface between the phases will move or change depending on whether the reactions are taking place or whether the phase of a particular material is changing, all right. So, now you have the other what is called a primary phase and what is called a secondary phase. Okay. So, to give an example, suppose you have a dilute solution of coal and air, what is the primary phase? Air, and the secondary phase is going to be coal. So, which means is that what is the dominant phase in a multiphase flow? That is called a primary phase, the dominant phase. Dominant means majority of the volume is occupied by that particular phase. So, that is called the dominant phase, and the other one is the secondary phase. So, you can read all this instead of my going every line, that what is the important aspect of this which I am capturing in my discussion. So, now there is I have already mentioned, because the method that you are going to use, what is the goal of a method? What is the goal of a physical problem? You want to formulate a physical problem with the simplest possible mathematics. But what is the characteristics of that mathematical formulation? You should capture every physics that you want. So, if you can capture the physics of the entire problem in the simplest mathematical model, then you are a genius. if you capture the very simple physics and have a very difficult mathematical framework, you are not only you are not a genius, you are not really applying your common sense. Okay. So, our idea here is to capture the physics of multiphase flow, the important physics of the multiphase flow with the simplest model, and that is why a few minutes ago we had a discussion. We said there is a method called DEM, there is a method called DPPM, there is a method called two fluid model, there is a Euler-Euler model. Some of the people who are more familiar with it, what are those mean? We will go over it. What it means is that what is the status of these phases. So, if the primary phase is so dominant that the secondary phase is very less dominant, then that is what is called a dilute phase. So, here this is a very important thing, how dilute is dilute mathematically. So, the 10 to 15% is maximum for a simpler method, otherwise it becomes dense. So, the volume fraction of a phase is the volume of the phase in a domain divided by the total volume. Okay. And so, this whether the phase is dilute or dense is important. The other problem which is important is whether the flow is laminar or turbulent. So, all of you, I am assuming that have some background in CFD and some background in all these codes. Whenever you have a turbulent flow, it is more complex, but unfortunately a large number of flows are turbulent in some way or the other. So, how do you model the turbulence? The real situation is that to model the turbulence of a single phase itself is a very difficult problem. Modeling the turbulence in a multi-phase, very few people understand that even today. So, if you want to spend rest of your research career, you can solve this problem, and that is how to model the turbulent flow accurately for a multi-phase. So, first of all, the governing equations, that is the mass conservation, the momentum conservation and the energy conservation. For a multi-phase flow, let us consider only two phases, not more than that, because we want to conceptualize the key ideas. What happens? If you have two phases and you have the multi-phase flow, your equations double, and the way you do the Reynolds averaging for modeling the turbulence, it creates a large number of terms that you have never seen before in your life, and nobody knows how to model them. So, what people say is do whatever you have. I mean, that is the way it is, you know, that is what we call jugaad, right? Do the best you can, but if you have time, you know, and somebody wants to feed you to do this work, whether it is a government or it is industry or your university, then you can say, okay, I am going to do this problem and solve it. Now, this aspect, how do you do the Reynolds averaging for a multi-phase or a two-phase system, and what are the additional terms that come along when you do the Reynolds averaging in the presence of turbulent flow. I have a complete PPT for that, but it is so mathematically complex that I just decided not to even include it. And then once you have those Reynolds average terms, then you want to decide, you know, how are you going to do the turbulence modeling by doing, say, what is called linear eddy viscosity models or some other, you know, more complex nonlinear models. Then only God knows, you know, what you will do, because there is no validation data, correct data, and the number of constants and number of things that flow around in these models is enormous. Those of you who are familiar with, you can appreciate what I am saying, but people are working at it. Very, very smart people are working at it, and I said that this is a big research topic. And initially, when I was thinking of doing that, I thought maybe I will spend a lecture, but later on when I looked at the equation myself, I myself got so scared. I said, I don't want to scare the kids in the class. All right, let's not include that. Okay, but you should be cognizant of the fact that turbulence is a very important part, and people are doing that, but they are doing with whatever they have. All right, and not going into more special, more particular treatment. All right. So these are the things that are important. There are very few flow that are laminar. There are some low speed bubbles that move, like in this book they are mentioned, which the speed is really small, which means that the Reynolds number based on the diameter of the bubble is of the order of about few hundred. Then you can consider the flow to be laminar. But as soon as you consider the surrounding fluid in a bubble column where the bubbles are formed, or in a bigger container, the Reynolds number for that container is about 4,000 to 5,000. Okay. Those of you who have worked or have known about the turbulence, what is the Reynolds number in a pipe when the flow becomes turbulent? Single phase. Yeah, it is between 2,300 and 4,000 if it is a smooth pipe. If it is a rough pipe, it could be earlier, but 23 is a borderline where transition starts, and 4,000 of course is certainly turbulent. But after 2,300, that regime is so difficult. We are talking only laminar turbulent. If you bring the transition into it, you are causing even much more difficulty. But only thing I want you to remember is the first part, that is dilute versus dense phase, because that will decide what method to choose. What method to choose. The second is laminar versus turbulent. As I said, most of the flows are turbulent, but there whatever you have in COMSOL or ANSYS or whatever code you have, so be it. That is all you can do. All right. And if you are very ambitious, like our three friends in the front, all right, whom I had dinner with last night, they were talking about LES and DNS and DES. I will leave it to them, all right, because if they have any of these things, they can tell me, look, it does not mean people are not doing that work, they are doing it, and they are thinking something new will come out of it. So these are all research problems, but I am talking about people who want to do any practical problems and what is the state of the art. Okay. So developing subgrid models for LES and doing DNS, as we were talking yesterday, you are talking about maybe you will become my age and still I do not know whether you will have that. All right. Okay. So now I will give you some examples, and there are some other ideas that are very important. So in multi-phase flow, where you have the phases, like the one is shown on the top and the other one is shown at the bottom. So the top one that you see is more like air and water. Okay. So this is your water, whether it is on the surface of the river or it is on the surface of the ocean, and this is the air. So you always have some waves, and because of the waves you have these undulations, and also because of the water that you have at the sea, it is always stratified. So you can have what you call a stratified multi-phase flow with air and water interface, and you have this undulation because of the wave. And in this case, if you apply the volume of fluid method, because these waves keep moving in time, you will find that the volume fluid method, the interface will keep on changing. It will not be a permanent interface like this, it will keep on changing. All right. This is a simpler model, it is not that difficult. Okay. Or this is also called the free surface flow, but I have put it in the context of the multi-phase. This is what is called, you have a bunch of particles, it could be solid particles. It could be oil droplets in water, it could be little droplets, which means a liquid, immiscible liquid. So, then you have this kind of a dispersion. So, what do you see here? You have little droplet, a bigger droplet, and they can be any shape. So, this droplet can be circular droplet, it can be elliptic droplet, whatever shape it may take depending on the forces that are acting on it. Also, you will find a little droplet, big droplet. So, if you have this kind of a situation and you want to analyze it in detail, that physical model is going to be extremely difficult. If you take the details of this droplet and interfaces between them and try to deal with this problem with surface tension effects, and even if it is immiscible liquid of oil and water, is going to be a very tough problem. So, now here are two ways to look at it. One is called the monodisperse, where you assume that all the particles that are there are spherical particle of some size. So, you can say some average size, not very little, not very big, you can say some average size. But even then you may have too many particles. So, then what you can do is that you can combine them together and you have a parcel of particles. So, you can say, okay, let me combine these 100 little droplets and create a big droplet, so that there is a bigger size. So, that is called a parcel concept to bring in, so that you can handle this problem theoretically, numerically. Because otherwise, if you have 1,000,000 droplets, I mean, how are you going to analyze them? So, what I am saying is that in multiphase flow, it is very important to take a physical problem and try to see that how to simplify the model, so that it is doable, it can be calculated. Okay. That is important. As I was giving an example this afternoon to Abhishek, I said, you have this room and you want to understand the air conditioning system, how is it working in this room, right? Now, you look at this room and you say, okay, I want to see the air conditioning system. There are 2 vents up and 2 vents down. Okay. This is called overhead air conditioning system. And what is the goal of this system? Goal of system is that the air is coming, it should mix with the rest of the room, and then because of buoyancy it goes up. Okay. So, now he says, well, I want to have all these chairs included, I want to have this thing included, I want to have this thing included, and somebody says, oh, this is not enough, I want to have in this chair also the legs and hands and everything included. Well, you can include it, we will wait for another 20 years for you to include all that and give me the answer. So, the idea is, what is the physical model you are interested in is that the air is coming, mixing with the current fluid and then taking off, and by mixing it hot with the hot air, it will cool you because the cold air is coming. And then after this air becomes warm, half an hour later the air conditioning system should again pump the air and keep on doing that. And for that you can consider the whole room as a single block or box and analyze it, and that will give you reasonable answer. Similarly, here what you need to do is, you can see that if there are thousands and thousands of these little drops, how do you basically deal with it? Now, these drops can be solid liquid like oil, or it can be a bubbles. So, in a lot of problems there are bubbles that are formed, like in cavitation the bubble is formed. How do you take into account these details? And so, that is a modeling. So, here what we call is a polydisperse system. Polydisperse means that everybody is different. So, all these drops, all these bubbles, they are different, and a monodisperse system we will assume that they are of the same size, same diameter. Okay. So, that is another terminology. These are all definitions actually. Yeah.
But in principle, when you want to solve this system, simulate the system, suppose we are considering a polydisperse condition, ideally each particle has to be treated as a separate criteria, and for each particle you have to formulate a separate Lagrangian equation, right?
It depends on what you are looking at. So, for example, as I said that if you have a combustion problem and you are looking at a combustion of very fine dust of coal into air, and from air it will take the oxygen and burn it, right, that is the combustion, simple, and you are considering a boiler. How many coal particles will be there? Give me a number. Billions. Can you imagine that taking a single billionth one particle, which are billions, and trying to calculate the forces on it, try to apply the Newton's equation, mass times acceleration is equal to the force, and it will have all kind of collision forces, it will have a lift forces, it will have a gravitational forces, it can have all kind of things that you have to account for. Then you will have to go to another janma. Okay, you have to take rebirth. It may not be bad idea actually. At least your rebirth, you will be again a scientist, it is assured, right. So, what you do here is that you take the parcel concept. What is the best physical model that can capture the process of fluidization that you are interested in, which means 100,000 particle may be enough. So, what you do is that you have a small laboratory scale experiment, which is done by in a virtual space of your computer. So, you say 100,000 is enough, but you say I have a very small laptop, I cannot do, sir, 100,000 is too much. Okay. I have to go to this wedding, I have to do this, I have to have this social commitment, and you are asking me to do 100,000 and get me the answer 1 week. Okay. You can take 10,000. So, that is where your ingenuity comes in, that is what is called a particle approach, a parcel approach. So, people have developed what is called a parcel approach, is that if you combine these particles to 100,000 particles, so let us say into 500, even then you can get a answer which is okay. If the answer is not okay, you do not do it, answer is okay. So, that is the approach you have to take. No, that is again I am saying that the method that you are using, there are number of things that are involved. So, suppose you have parcel size and you want to use DPPM, the total number of particles is smaller, but there are two criteria. One of them is that the total volume fraction should be small enough that you can use DPPM or two fluid model. The second is that the mesh that you are going to use should be such that that can deal with that parcel size. But if you have a very little particle, the mesh will be very fine. Okay. So, there are number of numerical considerations that you have to do, and of course, a lot of people who have done this work, you can rely on their experience to see what is the particle size. So, when I talk about the last presentation, hopefully, then I will tell you how to determine the particle size. Given a diameter, given the fluid velocity, fluidization velocity, etc., I will give you the expression that you can use to determine the particle size. Okay. There is a work done actually by a couple of people who came up with the concept, about many years ago at Northwestern University, and that is how I will give you that reference also, but at this point I do not want to go into that detail. Okay. So, you can see that what is the important thing which is written here, size and geometry. Okay. So, a lot of these simulations you cannot do at a very large scale, simply because the number of particles is too large, but you can get enough information, all right, and that information can be enough for the design. Okay. So, those of you guys, and I am assuming that all of you have, because I wanted an introduction which I did not do, those of you who I assume all of you are engineer, right, mathematicians, whatever it is, they are all the same. What I want to know is that if you are trying to do the experiment in a small scale at MNIT, right? Suppose you want to design a aeroplane, okay? You want to design 737, 787, big aeroplane, or let us say a car. How are you going to do that? Are you going to, if you have to do experimentally, what would it take? If you want to design a 787 which are flying, Air India flies them, right? Huh? So that is the answer. So if you suppose you said, oh, I have, I'm going to take this whole aeroplane in which 300 people can sit, and I'm going to build a wind tunnel in which I will put this plane, and this plane is flying at about 500 miles an hour at altitude of 40,000 feet, and I am going to create all that condition in the wind tunnel. Let us suppose you did it. Somebody gave you $200 million to build that wind tunnel, all right. So that will be about 75 crores. Somebody said, maybe 150 crores actually. Somebody gave you, said, we will build a wind tunnel. And you created all that. You know how much power will be required to run the air in that wind tunnel? The amount of power that will require can lighten whole of Allahabad. To have a velocity of even 200 or 300 miles an hour in a wind tunnel of that size, the amount of power to push that air will require the power plant which can take care of the entire Allahabad. So either you run that wind tunnel for MNIT and sleep in the dark without watching any movies. What will you take? The answer is clear, right? So the point I am making is that this is an important part here, the size and the geometry and the volume fraction. Volume fraction is a very important parameter in this one, and we will discuss that. What is the volume fraction? So suppose you have air and coal, all right, or let us say a gas and coal particles, okay. The volume fraction means that the fluid that occupies the most space. So suppose you have a pipe, so it means that maximum space will be occupied by gas. So that area of occupied by the gas or air divided by the total area. So you have a pipe, the area is pi d square by 4, right? D is the diameter, and out of that the gas occupies 80%. So what is the volume fraction? 0.8. So volume fraction as we move forward will be a very important quantity. So when you do the, whether you do the computer experiment or you do the experiment in your lab, you have to see what is the size and geometry and what is the volume fraction. So normally people take a simple pipe, it's a nice geometry, and then depending on what your needs are, you can decide what should be volume fraction. I am giving an example of air and coal, but you can use anything you like depending on the application you are in. So suppose you got all this, what is the use? Its use is not to write a master's thesis or PhD thesis. What is its real use? As I said, the real use is to be able to design the full scale plant. So when you are trying to build an aeroplane, you want to do a small model in your wind tunnel here in the lab, very small toy model, toy size, model you can bring in, run the air, calculate the pressure by using manometers. If you have now sophisticated LDV or PIV, you can do more detailed measurements. But how do you go from there to the full scale model? What from basic fluid mechanics, tell me what you do in the lab on a small model, how do you relate it to the big model?
Model analysis.
It is called a similitude. So, you apply the similitude analysis, and the similitude analysis requires that there is a correlation between the geometric parameters of a little model to the prototype, and also it ends up with keeping some quantities the same. And so, it may turn out there are some non-dimensional parameters, and the one of the most important one is the Reynolds number. So, you have to see that how to apply that similitude accurately, all right. So, how do you create a similitude? Anybody knows the method?
By keeping the Reynolds number of the prototype.
The way you do the similitude is what is called the Buckingham-Spy theorem, all right. So, use Buckingham-Spy theorem. So, you can use the Buckingham-Spy theorem to multiphase flow. So, instead of Reynolds number and Mach number and geometric parameters, you see every quantity, like in case of a aeroplane, lift and drag, they are the two important ones. They are a function of only three type of quantities. One is the geometric parameters. The geometric parameters in that case will be related to say wing shape, all right. That is the most important one. You can simplify that, and the other parameters are the parameters of the fluid. So, the density of air, viscosity of the air, speed of sound of the air, and the third set of parameters will be the flow parameters, that is velocity, temperature, pressure. Same thing you can do here. In a multiphase flow in a pipe, what is important? There is a gas phase, there is a liquid phase, there is a pipe diameter, there is a pipe length, etc. So, you know the people who have these pipelines, like India is trying to get a pipeline from Middle East via Pakistan, right. It is not coming to flow the oil. You know how much is the diameter of those pipes? Just guess. No, 500 is 500 what? Huh? 500 what? 500 half a meter is nothing. It's about 10 to 20 meters. Okay. So, it has a huge pipes. So, now you are starting from Middle East, let us say to Punjab, okay, get into India. How much is the mileage? Just guess that 2000 miles. So, you have a 20 meters pipe, right, and you have the length of the pipe is about 2000 miles, which you can convert in meters or kilometers, whatever you like. Okay. So, it will be about 3200 kilometers. You have to apply enough pressure to overcome the friction of those pipes, and those pipes are very rough. So, there is a lot of friction, there is a lot of turbulence, and there is a lot of multiphase. There is a lot of oil, there is a lot of air over the oil, all kind of conditions will be there depending on how much pressure you put in. It is not free. You have to have almost a very large amount of power to push against the friction of the pipe all the way 2000 miles. How do you design that? All of you are fluid dynamicists, how do you design that? Same thing. You take a little pipe and put it in your lab, look at the whole analysis, length, diameter, oil, whatever you have, and then you say Buckingham's psi theorem, whatever you want to apply, you can relate that little pipe to the big pipe. Same thing we will be doing here for the multiphase flow.
Generally, that's the dispatch equation to be followed.
Hmm?
That's the equation.
No, 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 no,
Can be applied.
no, no, no. What I am saying is there are all kind of more complex equations that come in, okay, all kind of more complex parameters that come in. But I am just trying to set a stage for fundamental thinking and ideas, that how do you take these ideas to extend it to multiphase. If you have a flow in a pipe, all right, a simple air or water going inside a pipe, it does not matter if it is rough pipe, it does not matter if it is a turbulent flow. There is, what are you going to use to calculate the friction loss? Can anybody tell me from fluid mechanics? If I am asking you that this is the length of the pipe, this is the diameter of the pipe, this is the flow velocity, I want you, and this is the roughness, I want you to tell me in 5 minutes that what will be the loss, friction loss.
Using Modi's chart can be started.
Okay. What is this? Anybody else? What? What equation?
Laminar equation. So that is generally called Hagen-Poisson equation.
No, no, no. Hagen-Poisson, I said it is a turbulent flow. And how do you know that it is a Hagen-Poisson? Because first thing, now suppose this is the problem. First thing you have to ask, that given the diameter, given the velocity, given the material property, that is oil or water or air, you have to calculate the Reynolds number, which means u d over nu. U is the velocity, d is the diameter, nu is the viscosity, right? Viscosity divided by density, all right. Once you say the Reynolds number is over 2300, is transitional or turbulent flow. First thing you have to do that before saying it is laminar. You don't know the answer. Once you have that, then somebody said Moody diagram. Have you heard of, how many of you heard of Moody chart? So you take a Moody chart in any book, you put in roughness, this is my roughness, this is my Reynolds number, draw a line, you have coefficient of friction, you are done. Do we have a similar thing? Do we have a similar thing to Moody chart? You know, when Moody chart was developed in 1940s, and Moody chart even today is the gold standard. It is the real gold standard, 24 karat, no milavat. People have done theses in taking in Moody chart and coming with some analytical equations like Colebrook equation and some other ones. The goal in the multiphase flow is, and people are struggling to come up with a Moody chart. And as I will show you, these equations are so, these flows, even two-phase flows, are so complicated that there is no Moody chart for that. So you take my word for it, if you go home and come up with a Moody chart, you will become a famous man, all right. So I don't know what your name is, but you are from VIT, so it will become a VIT chart, right. So the point I am making is that all these things that you already know should be dealt with in the context of multiphase, and it becomes so complicated, the applications become so complicated, from bubbles to very strange flows like slurries and all kind of things, that as you will see that is a very rich area for a lot of research to do. But I want you to remember these things which are important, not rest of it is not important. What is a dispersed phase, what is a interfacial or a free surface flow, and what is a monodisperse, and how you deal with complexity. In a multiphase flow, one of the very important factor is how do you deal with the complexity. How do you simplify the problem so that you can do it even in today's modern computers and get the good answers. So, first idea is how to simplify the physics to the essential details with the simplest mathematical model, and then the next step is how to solve that mathematical model. And once you got good handle of that, I think you can do a very good job in solving a problem that is of industrial relevance. Okay. So, now I mean I am giving you some more examples. So, this is example that you have a mixer, you know, right, you have a mixer. So, for example, if you have a mango pulp and you are making a milkshake with ice cream, right, that is a big multiphase flow, all right. And of course, you know, you are not interested in analyzing a mixing a multiphase flow, you are interested in drinking the mango shake, right, you are not interested in all this, let somebody else worry about it. But I am just giving you that there are a lot of very important problems where a multiphase flow becomes important in a practical application. So, here I am showing you, so geometry is very important. So, what you see the geometry of these blades, the number of blades, here the blades are curved, here the blades are curved in a different way, and the way they do the mixing is very different. So, you see the phenomena, what is the phenomena that you are interested here in? You are interested in the mixing. If you can enhance the mixing by changing the geometry, that is what your goal is. So, you can do an experiment, you can evaluate the mixing of the particle with the main fluid, and that is what is required in a combustion. That is what is required in many other industrial devices, that you want to, even in a fluidized bed you may require that in some cases, that you want to mix the particles so that they also start flowing, not stuck, not agglomerate, they also start flowing with the flow, and that is why we call fluidization. So, the shape and geometry which I showed you in the previous slide, and also the volume fraction, and now here it is interest is a mixing. So, how do you do that? And there are a lot of applications, as I said, fluidized bed is the one we are going to talk much later, but it is one of the most important application in whole of chemical engineering. So, if you are a chemical engineer, you know what it is. If you are a mechanical engineer, you know somewhat what it is. If you are a mathematician, you can do the model, all right. So, everybody has a role to play. Physicists can also play a role. So, everybody can work together, but the problem is an important one from physics point of view, as I mentioned to you, and geometry plays a very important role. So, I am giving you the actual liquid particle flow, and this is the geometry, and this is the one actually I did some experiment with my student, and so this is a mesh, and here we are using a particle method which we will talk about later, which requires ANSYS with the capability of the discrete element method. Okay, it's just an example. We are not going to go into detail of that method right now, but just to show you that how complex the flow is. So, this fortunately video is working, you know, many times these videos don't work, but what you see here is that it is rotating at 600 revolution per minute, it is rotating at 500 revolution per minute, and it is rotating at 400 revolution per minute. And then you can see that how the mixing is taking place in the all these particles inside this particular gaseous medium. So, you have these little particles, in this case these are of course artificial particles, they are not cold particles, and but they basically show you, and there's of course these color lines etc. show where the pressure is high and then the pressure becomes low, and as the rotation is going on. So, you can analyze all these details, but the idea is that what is the method that you use here, and we use ANSYS, along with we use the discrete element method with the help of the particle or parcel approach, okay, and we will discuss that later. So, now I will show you that how a simple flow in a pipe can have all these patterns. Now, if we had simple air or water, and this is a vertical pipe, and if you look at any book including this book, it will show you that a simple flow of air and water, depending on the, and they are all the same size cylinder. So, diameter is same, size is the same. What is the thing that is varying here? What is the variable that is varying? So, what is varying is two things. One is the inflow velocity and the other one is the fraction, the volume fraction. Volume fraction means that, you know, how much is the fraction of water versus air. Okay. And of course, one more effect which becomes very important in multiphase flow is the effect of gravity. In a single phase flow, in many times, if this was air, the effect of gravity will be nothing. Okay. If it is water, some. Multiphase flow is a lot. Okay. So, the effect of gravity, whether it is a horizontal pipe or it is a vertical pipe, horizontal pipe effect of gravity is very minimal, but in a vertical pipe it is a very important factor in multiphase flow. Okay. Now, of course, some people are looking at inclined pipe, okay. Like our friends here, they are looking at inclined pipe. You can do inclined pipe and see what really happens. But what has been done in the past in the pipe flow, which is a fundamental flow, is all experiment. So, experimentally what is shown here is that all these kind of things can happen. So, you can see here lot of little bubbles, okay. And then you see too many bubbles. So, this is called independent bubbles moving around. This is a packing of all these bubbles, and this is called a slug flow. What do we mean by slug flow? Of course, this is an empty area, looks like. The definition of slug flow is that the bubble should be at least 1/3 or greater than the diameter of the pipe. Then it will form. So, this bubble that you have, this is a big bubble. This is not an empty space. This is a big bubble. So, if you have this kind of a bubble in a flow, that is called a slug flow. And of course, surrounded by little bubbles, but this is a characteristic. This is called a churn flow, and churn flow means that it has, you know, some kind of a feature which is looks like this, but the rest of it is as if somebody has stirred it up. So, it is very different than packed flow. And then is a annular flow, means that most of the bubbles that are forming near the walls. Okay. The kind of flow velocity etc. is such that they are forming near the walls, and in the middle they are empty, which is basically the gas. So, this is called annular flow, and then this is a wispy annular flow, means that it takes a very strange pattern. So, these are the all kind of patterns that the people have observed in the actual gas liquid flow. And if you have to calculate this, in the pre-CFD era, nobody could calculate this. And even now, people do the experiment. Now, we have enough charts which tell you what is the velocity, what is the diameter, etc., and then they take pictures. Okay. And then they say, yeah, I can see these patterns. All right. But they have a tremendous impact on the friction and also the heat transfer. So, we are interested in two quantities, and that is the friction that occurs because of this flow. Friction means on the walls, and that means how much pumping will be required to pump a slug flow outside. So, if you have a pipeline and that consists of a lot of these big bubbles, you are in trouble. So, this is not desirable, and so most of the time you like to be in this situation. So, you want to have a situation in a pipeline, and this you think you can do with the help of dimensional analysis. And then of course, you can do the experiment and you can look at it, and then you can do the scaling law using the similitude, and that is the practice that people did it even today. And so, if you look at this book, it has correlations, it has empirical relations, it has all kind of experimental data, and that is all it has. It does not talk about how to do numerically. Now we have the numerical tools to do these simulations, but even with the numerical tools that we have, it is not easy. Okay. So, I am not going to go over right now, I will do it when we go to the bubbles after 4 or 5 lectures, because right now if I want to go over that what kind of tool is used for number 1, 2, 3, 4, 5, 6, first of all I cannot tell you exactly in all the cases that it will work, but at least I can give you some idea which will work, but we will do it when we come to this stage. And so now these are some of the examples in the nature. As I said, the whole nature consists of nothing but multi-phase flows. So you have gas liquid flows. You can see that wave formation that I showed you on the ocean, and so when the wave breaks, you have multi-phase flow. So these are all the examples, and I am not going to go and spend time on it. You can read it as a homework, or if you don't want to, you don't have to. You can better watch some movie or not something. But luckily your TV will not work. My TV didn't work last night, so it was good actually. I could sleep. Now this is a ship. So here what kind of bubbles will come? Your ship, a shape, missile, or any boat, what do you get here? Liquid and air. What kind of flow is that called? Is cavitation. It's similar to turbines. So what happens here is that all these waves that you are seeing, but very close to the boundary of the ship, you have these little bubbles, and they are very dangerous because they cause corrosions, they basically reduce the efficiency, because it causes more friction. So it means you require more power to move the ship. So you want to remove cavitation. So that is an example of cavitation. And this is, of course, we are going to talk a lot about these little droplets. And as these droplets move in time, then t equal to 0, t equal to 5.4, etc., they break up into little droplets and so on and so forth. So droplet, the theory of droplet is so rich that hundreds of books have been written and thousands of papers have been written. You take a little raindrop and have it impact, it spreads. That phenomena itself, based on surface tension, is very complicated. I don't know how many of you have seen, you take a water droplet and put it very nicely, with the help of some kind of a pitot, what they call a peptide tube or something. The shape will be curved like this. So that will look like obtuse angle. But if you take a mercury droplet, the surface tension effect is totally opposite. So it depends on the kind of fluid that you have. So the theory of droplet, two droplets hitting each other, a small droplet, big droplet, energy transfer among the droplet impacting the surface. There are tons and tons of work that is there in droplet. So I will talk to you when we talk about droplet very quickly about what method to use to study droplet. And all the stuff that I will show you, you can do it by ANSYS Fluent. The only key is that a lot of the people in this audience and many others, they don't know what is this VOF is. And of course, that level set method is not even included in the ANSYS. Okay. No, but the way it is, if you apply it, you will find that maybe 17.2 version might have it. I am not sure. Okay, but I don't know how well it works. Okay, so this is the clouds that you see there, and now this is the one that you know already. Like if you have internal combustion engine, you have that little nozzle from which this spray of liquid comes in, and that mixes with your air to burn. And that is a concept of cold combustion, that is a concept of liquid atomization that occurs in internal combustion engines. So this is again a multi-phase flow with the droplets plus the air to cause combustion, and these are the example. Now this is a rocket combustion in case of a space shuttle, and you can see again the fuel is coming out, whether it's solid rocket or a liquid rocket. In this case, again there is a mixing of the air with the solid particles, and they combust together to provide all this flame which creates a thrust. So, these are examples of energy production or liquid fuel combustion, and again we will come back to it about what methods to use. So, these are environmental flows. Now, here you see the avalanches, the movement of snow from the mountains, and ash plumes, volcanoes, they are all sort of multi-phase flows. Now, this is a granular flow. This is a very good approximation, and we are going to talk in length. This is also called the Euler-Euler approximation, and these are some other example of a droplet, and then how it changes into shape of a crown, and by the impingement on the surface. So, all these cases just give you an idea that how rich the whole field of multiphase flow is. Okay, these are other examples. So, this is your sandwich stuff, this is a wood stuff. So, all the paint, etc., they are all multiphase flow. All the cosmetics that we use, the lotions, the Vaseline, you name it, they are all multiphase flows. All right. So, this is again sediment transport that can take place in the rivers, because you have all this gravel underneath the bed, and all this is a multiphase flow. It's a rough kind of a multiphase flow, but you have solid plus the river bed. All right. Now, nobody is going to use the, although these people who work in hydraulics, they try to model this stuff, but again you have to be very careful, because this is a very complex bed. Okay. So, having a good simple physical model is important. Now, this is a solid liquid flow, and some of this thing we are going to talk about when we discuss the droplet, that how the shape of the droplet can evolve over time depending upon that what are the initial conditions are. So, these are again very interesting problems that occur in case of, for example, sedimentation when it settles, or in case of turbidity currents. So, these are all the examples that I am showing you. Metal processing, there is a laser system that can be used in manufacturing process, and then that if you are having a manufacturing process, even when you have a lathe machine, those little particles that basically erase themselves. So, these are all examples of multiphase flow. So, this is just for your information. Okay. Aerosol in the air, pathogens, viruses, they are all multiphase flows. Okay. So, now this is an important part that you have to the minimum bubble size for a flow to be classified as a slug flow is, it should be 1/3 at least of the diameter or larger. Then it will form a large bubble, and that is what we call a slug flow. Now, these are all the different names for it. So, you have a little bubbles surrounded by a gas. These bubbles can be liquid, then it called a droplet flow. It can be simple gas bubbles, then it is called a bubbly flow, and if it is solid particles, then it is called a particle-laden flow. And so, it can be considered as a cold particle surrounded by the gas or air. It can be a little oil particle or some other droplets, or it can be simple bubbles. So, same different names, but the schematic is the same. Annular flow, I already told you that most of the action is near the wall, and so rest of it you have basically gas, most of the liquid is close to the wall, like a thin film or a thicker film. So, annular flow, and this is a free surface flow that I already showed you, air water interface. So, these are the various type of flows, but they are all characterized by one thing is you have to account for the effect of surface fraction, you have to account for two phases, liquid or gas, liquid or gas and solid, and there are different methods to do them, because you have to take into account whether it is a dilute flow or it is a dense flow, and it is laminar or turbulent. Now, we already talked about these things primary phase, secondary phase, all this we have talked about. Now, how do you take the modeling? So, the old fashioned modeling to the complicated modeling, the most simple model used to be called algebraic slip model. They are very simple one dimensional models in the sense that they have a single momentum equation, even in 3 dimensions instead of having 3 momentum equation, and they are based on area averaging. Then there is a two fluid model, and that is also called the Eulerian model, or it is called also TFM, two fluid model, or it also comes in the category of DPPM, and that is the two phase model. And now this is a discrete element model in which you have to chase the particles, and in order to make it feasible computationally, not too difficult, you use the parcel approach or some other technique to do it. Now, how do you choose this? Depending upon what is your goal. If your goal is to get quick answers, dirty answers, but the physics you can capture, you use the simplest model. So, in some cases algebraic slip model may be okay, in some cases two fluid theory is important, sometimes DEM is important. But I think if you are a teacher, I think you should know all right. If you are a student, you should know all. Okay. If you are a manager or entrepreneur, you do not have to know anything. So, you have a clear path, whether you want to be a student or you want to be an engineer or you want to be a politician or an entrepreneur, you can decide. None of them come easy, you have to lie a lot, right, to be a good politician. If you are not good at it, you will fail, right. You have to be corrupt a lot. If you are not good at it, you will fail. So, it depends on what your qualities are. Okay. None of them is a bad quality, you have to have it, right. All right. So, now there are other definitions that are important, and they are important in terms of the choice of the method. One is called the one way coupling, which means this is very dilute. So, this bunch of particles are there, most of it is fluid. It is called one way coupling. One way coupling means is hydrodynamics is good enough. So, when I talk about the nanofluid in lecture number 4, that is a one way coupling. You put in a few particles, that is good enough, all right. So, that is like, for example, if you are a magician, right, and you must have seen this, you have a cup of water and they put some black pepper. The reason they use a black pepper is you can see it. If you put a salt, first of all it will melt, you cannot see it, but you put a black pepper, okay, and suddenly he says, all the children are looking at it as a black pepper spread, and suddenly the whole thing comes in the middle. How does it happen? They put in when nobody is noticing, some clear liquid drop, very little. Nobody even notices because they are looking at all these balloons and other things that this guy did something. So, what happens is that the surface tension between the particles and rest of the liquid, okay, that surface tension force changes by the liquid drop, and as a result of that, all of these little black pepper comes together. So, again the idea there is, but if you put in too much black pepper and if you put very little of surfactant, it is called, then your magic will fail, all right. So, the point I am making is this is called a single coupling, which means hydrodynamic model is good enough, and the effect of this is you can ignore almost. The two way coupling is that you have a little more number of particles, which means that these particles influence the hydrodynamics and the hydrodynamics influences these particles. So, the coupling is both ways. So, hydrodynamic change in the flow changes the forces on these particles and the other way around. So, that is why it is called a two way coupling. And then you have four-way coupling, which means that not only these particles are influencing the hydrodynamics, but they are influencing each other, means they are fighting with each other, all right. So, they become a four-way coupling, all right. So, they are fighting among themselves, colliding with each other, and also they are fighting with the hydrodynamics. So, then this is called a four-way coupling. So, it means that here of course, you have to use a very different method, and the best method for this kind of a problem is the partial approach or the DEM. This method you can do the DPPM is okay, Euler-in, Euler-in. And of course, here the one that we have here, just simple hydrodynamics, and if you can ignore them, just ignore their existence. But if you want to keep it, you can do it in a very simple way, as I will explain to you in lecture 4. And then there are all these other stuff that is there in a dispersed system, which means the little particles. As I said, you cannot deal with all kind of these weird shapes. So, most of the time when we have these particles, we deal them as circles, small spheres, they are okay. You can take average size of the sphere and then you can lump them also to make the computation smaller. And you can see all these particle-particle collision and dispersion and turbulence and etc., wall collisions. You can all handle them by having a good physical model. And then of course, the idea is what is the heat transfer if you have a combustion, what is the mass transfer if the phase is changing, and then of course, the composition will change, and if you have reactions, you have some other things. And then we have considered two phases. You can add some other phase also, solid 1, solid 2, but most of the time I do not think you should go there. Okay, it is just for your information. Most of the applications you do not need 3 phase. Chemical looping combustion has 3 phases. Okay, anybody knows about chemical looping combustion? There is a new type of combustion to capture the CO2 rather than a plant. So, it has two solid phases. One is the coal, other one is the air, which is gas, and the other solid is called the oxygen carrier. So, that is the one that has 2 phases of solids, and in a practical problem, and a gas, that is air. Other than that, I do not know many systems which has more than one solid. There are reactive flows, there are all kind of other flows, but I am sure that people can also find some other type of flows where there are 2 solids. But when you have 2 solids, they should be both important. It should not be that one is not important, then you do not have to consider it. Okay. So, there is algebraic slip model, as I told you, this is the most simple one. So, you basically solve a mass average equation for the velocity, and then you track the volume fraction, which is a very important quantity, that is the fraction of the gas divided by the volume fraction, means that this is a fraction of the solid particles in the whole system. And then of course, there are a lot of empirically derived relations that you need, because it is the most simple model. Okay. Nobody uses that anymore, even all these quotes that we have today, this model does not even exist. This is an old generation model before the advent of this new quotes and computers, but it basically shows the example of design of a reactor with a simple column type of bubble column. So, you have a liquid, could be air, you pump the gas, no, liquid could be water, pump the gas, it will sparge or disperse it, but you do not have any control how the bubbles will form, and these bubbles then move, gravity will also act. And so, what will happen is that the character of these bubbles that you have, and also the liquid slurry that you have added, they will have a very good mixing to get out. So, that is the reason that you use this kind of a bubble column. Now, this is an example of a churn flow that I mentioned, this is example of bubbly flow, but in those vertical columns that I showed you long time back. But this is the most important chart that people have been doing, and also this book has it, a lot of books have it. This is an old way of doing this, what you see here is this is called superficial velocity, all right. This is really superficial, all right. And what is this? Is a column diameter. Anybody can tell me what is the definition of a superficial velocity?
Assuming, suppose if you assume that only that particular phase is flowing, what would be the velocity? That is the superficial velocity. It's hypothetical.
Yeah. So, it is, if you have, let us say you know the mass of gas that is going in, or the volume of gas is going into this tube. So, the volume divided by volume of the gas only divided by the area, that is called the superficial velocity of the gas. If you take the liquid, liquid has a different velocity. You take the liquid volume of the liquid divided by the total area, that is called the superficial velocity of the liquid. And if you add the two, then what happens? Superficial velocity of the liquid plus superficial velocity of the gas, what does it make? That is the net velocity of the flow. So, this is important because what you see here is this is the superficial velocity of the gas phase and this is the column diameter. So, the column diameter is 20 and the initial velocity is small, what kind of flow you will get? I showed you all those columns, it will be bubbles. If it is a very large diameter and a very large gas velocity, it will be churn flow, turbulent. If it is a large velocity, but a small diameter, it will get a slug flow. And so, this is the kind of people did, and they even use today. They are handbooks, they have all this information. And I will, one of my chapters is dedicated to this. These are called the patterns or charts that are available as big handbooks, and people use that and they say, okay, I am going to design a pipe. I do not want this slug flow, this is bad. What I want bubbly, it's good, which means I can have a very large diameter, but the superficial velocity should be low. You can control that, you have a bubbles. And you remember that when I showed you those charts, the first one was bubbles and the second one was too many bubbles and the third one was slug flow. So, if I am the designer, I will say this is good, and this is what happens in most of the reactors, and this is called the fluidized beds, which create a bubble flow, all right. So, that is a desirable thing. So, now you have all these handbooks, forget about CFD and all this. You can all go home, said professor told what I want to know, I will check the handbook, tomorrow I am going to Sangam, all right, it is all done. It is okay. I think maybe you will benefit more by Ganga Snanam than listening to me, right. All the sins that you have done coming back from Tirupati or wherever you are coming from far away, VIT, it will all melt. So, if I have to choose, I will probably go for Ganga Snanam. Okay. And so, these are the various parameters that I showed you. The interesting thing that you find is that you see A, B, C, D, etc. These are the exponent you can determine exactly by using the Perkington-Spy theorem. Okay. And so, mass transfer and gas hold up and etc., you can go over and do it, okay, if you know the basic fluid mechanics. Okay, there are some issues mentioned here, I do not think that they are worth spending time. Then you can design the bubble column by using the simplest model called the algebraic slip model, in which you have only one momentum equation and one continuity equation, that is it. So, how do you apply a one dimensional momentum equation? You have to have a area averaging, and area averaging will allow you to apply the one dimensional equation. You do not get a bad answer, You can do it nowadays in 5 minutes on the computer. Because what is the continuity equation in this case? Tell me. If you, what is the mass conservation equation for this column? Simplest mass conservation equation, without any code or nothing, just the simple one, back of the envelope, 1 minute. What is the equation? You are more complicated. It is rho is the density, u is the velocity, area of cross section must be constant. That is it, you are done, finished. And what is the momentum equation? Momentum equation is rho u square is momentum, momentum in and momentum out. And what are the forces? The pressure in and pressure out times the area and the gravity. You can neglect the viscous forces. If you want to keep it, you can model that too. There is a friction law based on the turbulent flow, and there is a friction law based on the laminar flow. Whatever is suitable, you are done, you are finished, and you will get this answer. So, you see, in 10 minutes we are done. So, you have to understand what you are looking for, what is the physics, what is the goal. So, if you can get the answer in 10 minutes and this is your goal, not 10 minutes, but the right answer, and but you can get in 10 minutes, 5 minutes, 2 minutes, why do you want to worry about this $10,000 software and spend 6 months of your time? Okay. And so, this is other example. This video is not working unfortunately. So, this shows all these bubbles, and this is again the one video I already showed you, the mixing, and this is a Eulerian case. This is animation actually, and this morning I was trying, I do not know why it is not working. All right. So, now if you use the Eulerian approach or two fluid method, if you go into very deep physics, anybody is a physicist here? Okay. So, you must have heard the kinetic theory of gases. So, this is based on the kinetic theory of granular flow, and then once you take the kinetic theory of granular flow and apply the Boltzmann equation and use the moment method, and then you get the, the continuum equations, and then what you get is a Eulerian formulation. Okay. So, what I have said, have you understood that? You must have heard the Boltzmann equation, right? As a physicist, you must know the Boltzmann equation. That is called the mother of all equations. Okay. All the good things we always keep mothers in mind, There is, I have never heard of an equation as a father of the all equations. Boltzmann equation, every equation in the physics is derived from Boltzmann equation. Okay. Anyway, fluidized beds, risers, pneumatic lines, etc., particle-laden flows, etc., if they are dilute, you can do it by this method, and this is very accurate. This is excellent. Do not go to DEM at all if it is 10 to 15%. You can stretch it 20%, but there are certain tricks in it, and I will tell you in the maybe 8th or 9th lecture, and that is, if you have a particle-laden flow, the drag law, which now are available by several people who have worked on it. The oldest one is Gitzpaw, then Shyamlal O'Brien, and EMB is the best. You have to have a good drag law to calculate the forces on those particles. Okay. Now, this fluidized bed, as I said, I am not going to talk about here later right now, but we will discuss that in deep, in a very big way, because it is a very important part of chemical engineering reactors. It is a very important part of mechanical engineering. It is a very important part of physics and mathematics and computational science. But the main idea again is that you have a column, cylinder, you have some particles, and you inject some air. And the injection of that air is very important. it should be, if it is very slightly greater than the fluidization velocity, then you will get a bubbly column. If it is too large, then you may get a very strange column. So, you have to have what is called a fluidization velocity, which should be very close to the superficial velocity to get a bubble kind of mixing of the coal and the air, and then you can burn it, and then you can create the gas. Of course, it will contain CO2 as a major gas, then it will contain water, which will become a steam. Then you take that steam, put into the Rankine cycle, you generate the power, and then mechanical power you put in a generator, you get the electric power, you put in the grid, then you will have a light atom and an IT. All right, that is the whole procedure. Again, these are the various type of fluidized beds, depending on how much is the fluidization velocity, fixed bed, particulate regime, bubbling regime. So, this has a slightly higher than the superficial velocity. Slug flow regime is bad, it has a too much of a high velocity. Turbulent flow regime is also bad, because you don't want, we want to avoid as much as you can. A fast fluidization means you have a very high velocity, it kills us to annular flow. So, you can have all kind of the same patterns that I said is a function of two things. One is the amount of particles that you have and the kind of fluidization velocity, how close it is to the superficial velocity, and those parameters will define which is the right one.
What is there on y-axis?
Oh, y-axis is the high, oh, this one here, this is a pressure change. So, there is a pressure change in any pipe as you move. So, this is pressure gradient actually, delta P divided by the length of the pipe. So, the pressure gradient and how does it vary, this basically shows that. Now, to keep you a little entertained, let us try this. Let me see if it works. So, it is working. So, this is a bubbly fluidized bed. So, what you have is you have injected the air and there are some bunch of particles, and so it is bubbling. So, all these bubbles, you can see it, but is basically bubbling, and if you make it faster, that is the one that I showed you, then you will see that this is a faster one. You cannot see very well, but this will create a fast fluidized bed. So, it depends on what do you want. So, like I showed you here, it depends on depending on the application, whether you want this, which I showed you on the left hand side in the figure, or you want this one. So, you have these two type of patterns that can occur, which is a practical problem that I showed you in these two examples, taken from these websites which are written below. The applications, as I told you, are tremendous applications in mixing, in various kind of applications that I am showing you, catalytic hydrocarbon cracking, there is a physical context in heat transfer, solid mixing, gas mixing, and etc. So, there are a lot of applications that you have fluidized bed. Now, remember that is very different from cavitation, do not confuse with that. Okay, so, now these are some examples of that again you have a chamber, you have a gas in, it could be air, it could be some other gas, and then you have these particles which are shown as a schematic. Normally, you have a lot more, and then they are basically going there. This is a fluidization, which means then these particles flow like liquid, go up. So, this is a gas with entrained solids, then it can go here, and then the mixture takes place here. You can actually burn the combustion here also. So, it is a function of the bed depth, freeboard. So, there are a number of parameters that you can change to have the most effective fluidization. Effective fluidization means then you will have a better burn of the coal. All right. If you have chemical looping combustion, you have these iron hematite or oxygen carrier, then you have to account for the third particle also. This might be not clear at this point, but it will become clear later. So, these are some design parameters, which basically the geometric parameters of L over D, the length and the diameter, and then the superficial velocity, the number of particles. So, all those things have to be considered, including the effect of turbulence, to really model it and see how well the fluidization will take place, and that will determine how well the combustion will take place, and that will determine how well the power will be generated, and that will determine how much are the emissions from things like CO2. All right. So, this is again where to use CFD. All these things you can do with CFD: expansion, gas flow patterns, bubble size, etc. Once you do the CFD, you will have everything that you want to know, but you have to do it right. And one of the principle of doing CFD always, which I have been always emphasizing, all of you who have heard me yesterday and last year, is you cannot trust the CFD unless you have validated it. So, you must have either experimental data or some computation from somebody else that you know that you have done the CFD right, which means that your mesh is right, all the parameters are done right, the boundary conditions are right, and then you have reduced the data in a right way. Only then you can trust the CFD. And then again, what are the parameters? They affect the particle shape, which is circular in most cases, particle roughness, which basically is assumed to be smooth, particle cohesiveness, which means that we will not consider agglomeration, size distribution means that we can use a parcel concept or we can make a bigger size. So, all these things you can do. So, all these effects are lumped into the drag term to make the calculation simple. Okay. Otherwise, if you teach everything separately, you are going to be in trouble. Trouble means that it is going to be a lot of work, that is all. So, you want to make the physical model as simple as possible, so that you can get a meaningful answer. Okay. So, this is the animation of a fluidized bed, but it is not working. This is the kind of, from Fluent you can see that how the bubble formation is taking place, it spreads. So, again this is the picture that is taken in the experiment. You can see that the Fluent, and this was taken long time ago when even Fluent was not available. So, you can see that it matches quite well with the photograph, cylinder photograph of this particular simulation. Now, this is another system that I am showing you, gas, solid, same concept. It creates a annular flow, this is a bubbly flow, and this is now the newest research that is going on is to include a central jet. So, if you look at the latest literature in this particular field, people are doing simulation with a jet, because that allows for a better mixing. Okay. And so, this is a single jet versus twin jet, and I will show you some video. And so, this is the simulation that my students have done, and so I think this is a double jet, this is a single jet, and so this is a single jet simulation that the students have done. I think it has about 150 160,000 particles, and this was done with a newer code that has come along in a DAEM area. It is called Rocky. Have you heard of Rocky? Yeah. So, this is a new code, and so this code has been actually developed by the Chinese people. So, I do not know what the cost is, and it has not, but the advantage there is that you can do this kind of calculation. So, see initial situation and afterwards how the particles, and this is done on a single jet, and this is I will show you the video for a double jet. So, this is what happens, a double jet. So, initially everything is uniform, you inject the jet. So, you have two jets, then they keep on growing as the time passes, and so they allow a much better mixing of the solid particles with the hydrodynamics, and you can do it in Fluent. I mean, we can do in Fluent. So, this is doable. All right. So, now it shows the effect of the drag model, because that goes into the calculation, and it is very important because that shows basically whether your calculation is good or not. Okay. So, now this is the video. So, this is a two jet on the left hand side, and you see this is done with a simulation using Rocky, and that is a single jet, and the previous one was the still pictures. So, you have to only apply the right boundary conditions here. So, let us see if it is. Should be work? Yeah, it should work, you know. So, it depends on the flow rate, which is given in very small flow rate, increase the flow rate, increase it further, and the last one has the largest flow rate, and you can see in a given time for the same amount of time how much is the fluidization is going through this particular column, where you have a mixture of particles and the gas.
So it will work for only bubbling fluid, or it can work for, you can use it for any multiphase?
No, I mean this is for a bubbling bed, but you can try it. You know, I mean, I cannot say what will happen, but you can try it. You have to just increase the velocity of the jets and see what the effect is. My feeling is that it should work for, you know, most of the flows. I am not totally sure about the slug flow. Now, slug flow has such a huge thick bubble that I do not know how it will be captured, but my feeling is for rest of all type of flows it will work. So, this is the actually latest work, and we are going to publish it soon in Journal of Applied Energy, because the latest trend now is to try to use jets to enhance mixing and promote combustion.
What is the significance of different colors?
You know, the what you see here is they are related to the velocity of these particles, and so that is color coded. I do not have a color scale, but otherwise I will have shown you. So, what happens is that the lower the particle velocity is higher, and as they go up they become smaller and smaller. Now, the trick is that if you keep on going too much high, then with the gravity they will fall down, and so you have to suck them out around here, or you will have to start the combustion around there. You cannot allow the particle to again fall back because of gravity. So, they are color coded with the velocity field.
This is most of the I think symmetric configuration, but the pattern which is developed now remains.
Yeah, so this is we have a experimental data also done in this, and so the experiment was actually done in China, and they found, you know, that it should be, if the jet velocity is the same, everything is the same, it should be a symmetric pattern. So, this non-symmetry develops is because of the way the numerics is done. In the truncation error of the numerics, there is some small error that it develops. We try to investigate that problem. Is a very good point, that there is some small asymmetry. Now, in general, if we add a higher size mesh, it will not show up, because then you are hiding it, and this happens even in a single phase flow. That depends upon, you know, how are you doing the calculation. Like for example, if you take the whole pipe and go from 0 to 360 degrees in circumferential direction, in what way you go, this way or that way, and you have a finite volume mesh on these slices from the center to the periphery, it turns out that once you are doing that and coming close to 0 to 360, it should be identical. But if you are doing finite volume, there is a small discretization error occurs, and as a result of that, the small asymmetry can occur, but you can minimize it. I mean, if you look at, you know, here, it starts out fairly symmetric with some asymmetry, and this thing also observed, not because of this reason. In experiment, you know, the way you take the data and other things, you can find, you know, not exactly the same pattern. This is much more, you know.
Experiments may come asymmetric.
Yeah.
But I think in numerical.
Yeah, it should not be. Yeah. Now, this shows the effect of the drag law. So, if you look at the effect of the drag law, which affects the motion of the particles, you can see that how different the flow is. So, what it means is that all these minute details that go into, which are basically a part of the drag law, and that is where a lot of research is going on. Like it started with Gitspaw and then Shyamlal O'Brien. I gave you two examples, and EEMM which is the latest version. I don't know the whole expansion of that acronym, but people are keep on modifying it to see what is the best one. So, in this case, if you look at this, it turns out that this is a better drag model than this one. So, this basically concludes this particular basic introduction to what the model is, now what the multiphase flow is, what is a dilute suspension, now what is a dilute, what is a turbulent, what is a laminar, what are the various patterns can happen depending on the velocity of injection, what is the fluidized bed, what is the effect of mixing. You can mix it with a rotor, and so all these examples that I have given you just to give you a flavor of what is happening. In terms of the modeling, we have already discussed, that algebraic model, nobody is using that ASM. It is very simple. You can give a homework problem to the students. The other models are much more complicated, but they are all built into Fluent or CSX or maybe other codes. There are other completely multiphase flow codes, one called MFIX. Has anybody heard of MFIX? So, that is a code that has a lot more capability. There is other code called Barracuda, very expensive code, but it has a lot of capability. As I said, Chinese have come with their own code called Rocky. They are all good at efficiently doing the DEM. For TFM, Eulerian, I think Fluent is good enough.
In this fluidized type combustion analysis, whether that heat transfer is also considered or only fluid?
No, heat transfer is considered.
In that case, like
There are two
property variation with
yeah,
time
there are two kinds of, they classify as two kind of flow. One is called cold flow, and one is cold, and one is called hot flow. So, if you are interested in only looking at, you see what people do actually, if you look at, there are a lot of, in India there are not too many people doing that, but what they do is they take a little column, you can actually set it up with very small amount of money. You can take a plexiglass column and you have to have a little hole to inject the air, and then instead of using coal, etc., all this stuff, they take a little beads, little beads like glass beads of some size, small size, and then they see how the fluidization is affecting that glass beads, how they move up the column. Of course, the glass bead, their weight and their density and their gravity, etc., is different, but it can give you some feeling about the flow field. They can tell you about the kind of pattern that will develop, but the real flow is a hot flow. So, hot flow means that the temperature of the reactor at which the combustion will take place. Can anybody tell me how much is the temperature? Anybody who has worked with boilers or coal or something? That is correct. You are very close. It is about 900, 800, 900 something. So, 900 degrees centigrade is the temperature at which that reactor will have to be kept. So, you have to be very safe, you do not want to touch it. But then you have a real cold particle, and then you have a real air going in, and the oxygen will do that. Now, still you are stuck with nitrogen. So, what chemical looping combustion idea does is, they say take a vacuum chamber of the reactor, put in the coal and put in what we call the oxygen carrier, they call it. What is the oxygen carrier? Cheapest one is iron oxide. So, it is Fe2O3, or you can put manganese oxide Mn2O3, or you can put cobalt oxide CO3 or something, right. So, most cheapest oxygen carrier with good properties is say hematite, they call it Fe2O3. Now, there is no nitrogen, nothing. So, the oxygen is supplied by the breakdown of a reduction reaction of Fe2O3 into Fe3O4 plus O2. That O2 is now a pure O2, that is the idea of oxycombustion also, and that reacts with the coal. And now you have a pure coal interacting with pure oxygen. So, what is the byproduct if a coal interacts with a pure oxygen? Pure CO2 plus H2O. H2O becomes a steam at 900 degrees, steam, it becomes a steam at 100 degrees actually almost, but 900 is pure steam with a very super steam. So, what happens is that the CO2, which is 99.9% pure, you can capture it. So, this is called CO2 capture, and then you have choices. So, you can send it to the chemical industry and they can make other chemicals, or you can say I want to get rid of it. So, you can put in the pipeline, put underground. So, that is called sequestration of CO2. Okay. And so, this CLC, which is a new technology, the advantage here is that it is almost CO2, you do not have to get into the atmosphere anymore. In the standard boiler plant, all this particulates and everything goes into outside and it is polluting the whole air. So, you are using a oxygen carrier, decomposing into oxygen at 900 degrees, interacting with the coal, creating CO2 plus H2O and nothing else. You are taking the CO2 away, H2O you are sending it to the power plant, which may have a Rankine cycle or whatever, heat cycle, generating the mechanical power through the gas turbine or whatever turbine you have, and then generate the electricity. And then CO2 you have captured, now you can put it underground or you can do the chemicals whatever you want. So, this is what is called the chemical looping combustion, that is a new trend for the future power plants. So, that you are not polluting the system and the atmosphere and you are keeping the climate under control. Now, no, you have to take everything into account in the modeling. You have to have a reaction. So, you have to put the reactions into the system, they are all there in the fluent. So, fluent knows that people need it. So, they have their own experts, they are keep on putting that, and they are relying on people like us. So, they give us a few small change, from which we can buy ice cream, and they say, okay, you give a ice cream to your student also and he will do all the job. And then they take all this information and then they improve that. Okay. So, there is a lot of depth now in CFX, MFIX, all these multiphase flows to do the sequestration problem. So, there is a code known as stuff 2 that I am going to be talking about in the 8th lecture, and this MNNIT student Abhishek Gupta is working with me to use that multiphase flow for sequestration. And so, you will see what the thing is involved there. So, these are the new trends to control the CO2, but if you put the reaction, it is not a, it is a more difficult problem, but it is not a hell of a lot difficult. Yeah, it is, let us say 10-20% more difficult, because all this thing is built in, but you have to be sure that click in the right place. One of the things I always am scared from the young people is that they click too fast. Okay. So, sometimes I have a problem with the computer and I say, can you fix it? So, first of all, I cannot figure out what they did, and after the end of this my computer is worse than what it was. And the reason is they click so fast, neither I understand what they did and also they mess it up. And once they have messed it up, then they say, sir, it is your problem. Now, I mean, this is all just fun and games, but what I am saying is all these things are doable. So, whatever I present to you is giving you a kind of the entire scope of what is going to be taking place in this course, and but we don't have much time. So, a lot of you will have to rely on what you get. Okay. And as I said, this itself is about 60% of what I could have given you more, but this 60% itself is so much that either I go so fast that I flip the slides, which is not good. If you want, I can flip it, all right. Okay. Now, but what you get is a non-cooked food, right. If you flip too fast, like if you flip the chapati too fast, what will happen? It will not be cooked well. So, you will not learn too much. So, we will go at a pace, and don't worry about it, learning a little bit is better than learning nothing. Okay. So, I think that is about 7:30, and it is, I mean, I think to restart anything is not a good idea. So, we will start tomorrow, but tomorrow we will start on time at 4 o'clock, unless until you guys can come up with some ceremony, then I think it will be good. Then we can start at 5:30 again. But I am just kidding, if the director comes to know, he will be mad.